This video is the part 2 of our discussion on electricity under the physics practical for the 2022 Waec. So in this video, I'm going to demonstrate how to carry out the procedure we described in the previous video. So if you haven't checked the previous video, you need to check that to understand the experiment we are referring to and the procedure. So in this video, I'm going to simulate that. Although the actual experiment will be a physical one, but this software allows us to exploit without actually stepping fully into a physical lab. And it allows us to have various settings and get similar results as what you would get in a physical lab. So if you would like to get this simulator and to simulate these experiments, you can go check our website or you check our description for details on how to get it. So let's get started. So this is the first scenario we described in the previous video where the standard resistor would be in parallel with the resistance from the potentiometer. So we are going to walk through the experiment. But do note that in the actual experiment, the standard resistor is likely going to be in series with the potentiometer wire, but then the procedures are not too different in terms of how you move the jockey and how you take reading. The difference is just in terms of the outcome. The outcome will be different, but the procedures will be quite similar. You'll be asked to move the jockey, measure the value of X, take the reading for that, then take reading from the ammeter and eventually plot some graph. So let's look at this scenario and let's explore. But before we do that, let's check out the settings section. In the settings section, we're going to have our X vary from 25 to 85 and we reach a step of 15. Then we are going to assume that the internal resistance for this particular battery is 0.1 ohm. So every battery has some internal resistance. So in this case, let's assume it's quite low. Let's reduce to 0.05. Then the standard resistance is going to be a 2, then the EMF is 3, and so on and so forth. So the resistivity of the wire in this experiment is assumed to be 4.9 times 10 raised by minus 7, and that's the resistivity of a Constantine wire. This Constantine wire is a very common wire used in making potentiometer. Then we assume the diameter of this wire is 0.4 millimeter. Okay, so our time is going to be 30 minutes and let's start. So this is the simulation environment, and here we have the potentiometer, we have our jockey. Our jockey is this. If you zoom in, you'll be able to see the jockey very clearly. These are jockey making contact with the potentiometer wire. Then we have a switch that allows us to remove and insert the plug, and we have other settings. So let's get started. So for the reading, we're going to take reading when X is 25, when X is 40, 45, and so on. So let's start off with when the first one we do is to remove the plug. Very important so that you don't drain your battery. So let's move this to 25. So once we have it at 25, we turn on the switch, then we take reading. We try to take reading from the ammeter. So for the ammeter, note that each step on this ammeter is 1. So which means this is 4, this is 41, this is 4.1, 4.2, and roughly 4.25. So this is roughly 4.25. So this is roughly 4.25. So let's take for the second reading. Let's take for the second reading. For the second reading, when X is 40, we move this to 40. Then we ensure this is turned off after taking your reading. So when it's 40, we switch it on, then we take reading. So if you check closely, you see that this is roughly 3.25, roughly 3.25. So you record this as 3.25. Then the next reading is when x is 55. We move this to, you turn this off, we move this to 55. Then you take your reading, but before then you insert the plug, then you take your reading. So this is 2 points. You count. This is 1, 2. So we have, it's almost, this is 8, is almost 2.8. So let's say roughly 2.7. Let's say roughly 2.7, 2.77. Okay. So this is roughly 2.77. Then let's look at the case where this is 70. Then let's take reading. So this is almost, this is roughly 2.5. Let's check 1, 2, 3, 4, 5. So this is roughly 2.5. 2.5. Then the next thing to do is to get reading. Get the reading when we have 85. So this is 85. So what is the reading at this point? So this is roughly 1, 2, 3. So let's say 3, 2. So 2.32. So roughly 2.32. 2.32. So now that we've gotten all the ammeter reading, we take the reciprocal of x. So let's take all the reciprocal of x. So we've completed all the table. We've gotten the reciprocal of x. Now we move to the next phase, which is plotting the graph. So in this experiment, we're expected to plot the I on the y-axis and 1 over x on the x-axis. So let's go to the graph section. So here you have the value of I against 1 over x. So I is on the y-axis, 1 over x is on the x-axis. So how do you plot? How do you make a good plot? So I'm just going to walk you through how to make a good plot, especially how on paper, right? So to make a good plot, the first thing we want to do is to define the title of the plot. So the title in this case is plot of I versus 1 over x. That's the title. The next is to label the x-axis. The x-axis is 1 over x, and the unit is centimeter raised to the power of -1. So we can just simply put it this way, right? Then on the y-axis, the label is I, that's amp. Then the unit is the amp, so which is A, right? So we've labeled all our axes and we've also set the title. The next thing about making a good plot is to figure out the scale. The scale is the most difficult part. So how do you get the scale on the x-axis and the scale on the y-axis? So let's start with the scale on the x-axis. To get the scale on the x-axis, you identify the maximum value and the minimum value. But if you want to capture the intercept, whether the y-intercept or the x-intercept, your minimum should be 0. Just aim at something around 0. But if you are not interested in the intercept, then you can just use this to be your minimum. Since we're interested in the intercept, we're going to make our minimum to be 0. So if you take 0 out of this, you still get 0.04. So now, we want to divide this by number of divisions that you expect to have. If your graph has 5 divisions on the horizontal axis, then you will divide this maximum, which is 0.04, by 5, if 5 is the number of division. So in this case, I'm going to assume I have about 4 to 5 divisions. So if I have 4, for example, it means my spacing will be 0.01. In other words, if you divide this by 4, you get 0.01. So that is how you figure out the scale. You take the difference between your expected maximum minus the minimum you're expecting to be on that axis, divide by the number of division, major division on that axis. So that's how that's the rationale behind what I'm going to type here. So I'm going to use 0.01, then I'm going to stop at a point that is close to this value. So I'm going to stop at 0.05. You need to leave an extra space. You shouldn't stop exactly at the maximum. Then the step is 0.01. So this is my division on the x-axis. Then what about on the y-axis? You take this maximum. Then if you want to get your y-intercept, it's reasonable to assume your minimum to be 0. So since your minimum is 0, then you just divide this maximum by the number of division you want to have here. So let's imagine I want to have a division of 5 or a division of 6. In most graph paper, the vertical axis will have more division than the horizontal axis. So let's say I'm going to have a division of 6 along this y-axis. So I'm going to divide this 4.25 by 6, and that will give you around 0.7. Now we can't use 0.7 as our division because 0.7 is not an ideal scale. You should round it up to the nearest ideal. So the nearest ideal is 1. That is, if you round 0.7 up, you are going to get 1. If you want to know more about how to make a good plot, check out our video on that. We made a dedicated video on that. So we are going to use 1 as division here. Then we are going to start from -1. We are going to stop at 5. And we are going to use a step of 1. So now we have our scale on the y-axis. So now we've got our labels, we've got our scale. So now it's time to do the proper plotting. So to make a plot, the first step is to, after you are done with the scale, is to identify the points on the graph. So how do you identify the points on the graph? Using the simulator, I'm going to start by clicking this pencil sign. Then I'm going to look for the value of 1 over x when it is 0.4 and I when it is 4.25. So when this is 0.04, where is 0.04? So here we have 0.04, right? Then our I is 4.25. So where's 4.25? This is 4, then this is 4 points. This is 4.2, right? This is 4.2. Every small division here is 0.2. So this is 0.2 added to 4, that's 4.2. Then 4.25 is a little bit above here, right? So this is it. Then you click. In this software, once I click, it indicates that point. So the next is to look for 0.025. So 0.025 is going to be close to 0.2, right? Then you need to ask yourself, what is this small division? This small division is the difference between this big division by the number of small divisions. We have 5 small divisions here. So it means each of this will be 0. Each of this will be 0.01 divided by 5, which would be 0.002. So in this case, this is 0.022, right? That's what this would be. Then since we're looking for 25, is a bit above that, so this is it. Then the next thing you need to do is to go up, and we are going to 3.25. So this is 3.2, this is 3.2 here, then 3.25 is a bit above 3.2. Then that gives us this, it's roughly this. And the next thing we want to do is to move to the next, which is 0.18. So 0.18 is very close to 0.02. This is 0.018 rather. So this is it here. Then you go up towards 2.77 on the vertical axis. 2.77, this is 2, then this is 2.6, then 2. 8 is here, then 2.77 is just below 2.8, right? Then we have this. So the next is to locate 0.014 on the x-axis. So this is 0.012, 0.014. Then you move upward until you get to 2.5. So this is 2.5 is just right in the middle of 2 and 3. So which is here. So you want to click. And the next is 0.012 on the x-axis, which is 0.012. This is 0.012 here. Then on the vertical axis is 2.3. This is 2.3, then 2.32. So 2.32 is just slightly above 2.3. So this is it, and you click. Once you've gotten close to, you don't need to be 100% precise, just get very close, then you click. So this is our reading. So we've completed this section. On this simulator, once you've completed a particular graph, you're going to have a check mark telling you that you are done with the point. Then the next is to draw a line of best fit that connects all these points together, or that runs through them as closely as possible. So how do you do that? So you just on this, you just have your ruler. If you're doing it on paper, you have your ruler placed on them. Then you draw your line such that it touches as many points as possible, or it runs closely to as many points as possible. So let's see how we can achieve that here. So what I'm going to do here, let me clear this and start again. So I'm going to click somewhere here, then I'm going to try to connect as many points as possible. Then that's it. Okay, so this is my line of best fit. Then that's it. The next is to get a slope. To get to compute the slope, or to get a slope of any line, you want to ask yourself, where are the 2 points I'm interested in? So in this case, I'm going to choose 2 points that I will use to calculate the slope. So in this case, I'm going to pick this point. Then I'm going to pick, let's say, this point. Just pick any 2 points on the line of best fit. Okay, then the next thing is to identify those 2 points. So let's say this is point 1 and this point 2. So if this is point 1, what value is this? This for the y value of this is y1 and this is y2. So the y1 is this, which happens to be 2.6. So this is 2.6. And the y2 is this, which happens to be roughly 3.7. So this is 3.7. If you subtract 2.6 from 3.7, you get 1.1. Then what about the x1? The x1 is the value on the horizontal axis. So you just look at it downward like this, and that's roughly 0.015. 0.015. Then the x2 is this, which is 0.03. 0.03. If you subtract x1 from x2, you're going to get 0.015. So what then is the slope? The slope is the change in y divided by the change in x, and that's equal to 73.3. Then what about the y-intercept? The y-intercept is the point where this line of best fit touches the y-axis. So, and that's roughly 1 point. That's roughly 1.5. So that is the y-intercept. Okay, now that we are done with the intercept, the slope, and everything about the graph, the next question you'll be asked is to is you'll be asked some questions based on what you've done. So an example is this: you'll be asked to calculate a particular value given certain things. So here we're told that what is R naught given that E is 3, which is the EMF of the battery, and C is the y intercept. S is the slope. We don't need the S, we just need the C. So in this case, if I divide E by 2, if I divide this 3 by 1.5, C is the y intercept, which is 1.5, I'm going to get 2. So you'll be asked more questions. For example, you'll be given some extra questions, you'll be asked to solve some questions. So that is the last phase of this experiment that Waec will present to you. I'm not going to go into all of these parts. If you want to know more about how to answer questions, you can get this app and practice a lot of questions. So I'm going to submit to show you that this application is capable of grading every aspect of this experiment. So let's submit and let's check what we've got. So the graph axis, this is my score on the as regard the point, this is my score and so on. So this software is capable of monitoring every aspect of the experiment and also helping you to also guiding you on how to figure out the right scale and every other thing that you need to do. So this brings us to the end of this experiment, and wish you the best of luck in your exam.